Welcome to ExplainerCast, Episode 8. I am your host, Dave Smith.
And this is Shane Swenson.
And we have some explaining to do. Today, we're talking about eclipses.
Yes.
Everything you didn't want to know about eclipses is about to be yours to keep forever.
Yeah, at least if you're the type that they just sort of happen to. But if you start wondering why, then maybe this actually will be what you're looking for.
Yes. So, eclipse. Can I venture a fundamental definition of what an eclipse is before we get into all the mechanics of how they happen?
Go for it.
An eclipse is nothing more than a shadow cast on a celestial object by another celestial object.
Yep. And the result is that it hides the view of one of those objects, the one behind
the one
the
making
shadow.
the light.
That's right.
Yeah.
Yep.
Is it required to say that it must be a light emitting object that's actually on the other side of the thing casting the shadow?
No, I think generally it just means that one object is blocking really the view of another.
Ah. So a shadow is really just a special case of an eclipse.
I think so. I think, yeah, if at least one of them is making light, then there will be a shadow. But
right, but it's not required. In other words, if I can't see something because something else is eclipsing it, that's really the definition. It's not about the experience that we most often associate with an eclipse, which is this really cool shadowy thing that comes upon you in the middle of the day and makes the day dark.
Right. I mean, that's a super awesome type of eclipse. But yeah, I think my definition matches yours, which is you're obscuring the view of one object by imposing another in the path between you and that object.
Yes. So I can eclipse my own view of something by just putting my hand over my eyes.
Yep.
But that's not really the kind we're going to talk about today, because the mechanics of that are uninteresting.
That's right. A little too easy.
Yeah. Place hand in front of eyes, eclipse.
Done.
Next.
Next episode.
No, but there's some really fascinating and weird and hard to visualize spatial mechanics that happen when an eclipse actually takes place from the vantage point of someone standing on the Earth. And that's what we're going to focus on today, right?
Yes, exactly. And so the three objects in question are the sun, the moon, and the earth. And right off the bat, we have two categories of eclipses to talk about, and those are solar and lunar eclipses. So, Dave, have you seen either of these categories in person before?
In 2017, I was close enough to see the solar eclipse partially taking place from Canada,
Okay.
where I was at the time.
Yep.
And it was really cool to see, even though it wasn't a total eclipse for me where I was standing.
Yep. And so in that form of an eclipse, a solar eclipse, let's talk about which objects, what order were these objects stacked in? And so who was blocking whom?
Yeah, so it's really funny because there are three possibilities for the order of things generally when there's three bodies, but only two of them ever happen here. And I was thinking, if the silly answer would be, well, yeah, so solar eclipse is when the moon blocks the sun, and a lunar eclipse is when the sun blocks the moon.
There you go. There you go. Just talk.
Never gonna.
Just throw the moon
the
over
moon
on the
goes
other side of
by.
the sun,
Yeah.
right?
Never gonna happen.
Be a hot day.
Yeah, so a solar eclipse is where the moon blocks the sun.
That's right.
Right, where what's being eclipsed, to use the verb or participle form, is the sun by the moon.
That's right.
And then a lunar eclipse is something else. Actually, Shane, why don't you venture a guess at that one?
Yeah. So given that we only have two choices, in this case, it's where the sun is blocking the earth is blocking the view of the sun for all of the creatures on the moon, all the lunarlings. And
yeah.
so they end up in the Earth's shadow. And the way we see this on Earth is the moon gets darker and it turns kind of reddish. There's enough light kind of coming around the Earth being, I suppose, refracted through the Earth's atmosphere. And,
yeah, that's what I was going to say too.
Yeah, and maybe the blue is kind of being filtered and scattered out as well. Our atmosphere glows blue due to that effect. And the result is that some red light does get through to the moon, and so we see it in that form. So, on the other hand, in the solar eclipse where we pass through the shadow, what did you see in that case, Dave?
Well, I was standing in a high-rise building in downtown Toronto, and the sun and moon were actually at a pretty low point in the sky on the horizon.
Mm-hmm.
Kind of, I think it might have been afternoon or evening, and I was looking out the window, and the outside area got noticeably dimmer, but not darkened because I wasn't in the total eclipse shadow.
Okay.
But what I saw was when I would kind of squint through my eyes to not like destroy my eyes looking head straight at the sun, I could actually see the moon obscuring a big chunk of the sun visually. Like it was like a bite was taken out of the sun.
Yeah, exactly. Yep. Like turns it kind of into, yeah, like a crescent.
Like a crescent sun.
Mm-hmm. A crescent sun instead of a crescent moon.
Yeah, exactly.
Yep.
It was honestly really cool. And I was, at that moment, I was filled with regret for not being in the right place at that time.
Yeah, it turns out, and I had a similar experience a while back, that the difference between being in the partial eclipse region versus the total eclipse region is pretty dramatic. And so that particular eclipse, we traveled up to Idaho in order to be into the total eclipse region. And so we initially saw the same thing, which is that the moon progressively moved across the sun, casting or obscuring part of it, really. I was going to say casting a shadow of the sun, but that doesn't happen. And
Right.
and over time, it got closer, got a little dimmer, and then when the moon fully obscured the main body of the sun, what we associate with as being the sun, this relatively big thing in the sky, then that's the total eclipse period, and things changed very dramatically. Like at that very short time window, it basically felt like someone pulled a dimmer switch all the way down, and it became kind of nighttime dark, like kind of full moon nighttime dark. And then we could see what's called the corona, which is this glowing large gas area of gas surrounding the sun that normally you don't notice with the human eye because the sun is so bright, but we could see all of that glowing instead. As the total eclipse window was ending, you could actually see the brightness in the atmosphere coming toward us as the edge of the shadow was crossing toward us. And then as it passed overhead, sure enough, it got a lot brighter, like someone raised the lights.
Was it kind of like a sunrise on Fast Forward?
Yeah, but like measured in seconds. It just felt like a few seconds of seeing it coming, and then someone just brought the house lights back up. And sure enough, now there's a little sliver of sun. It was surprising how little direct sunlight it takes to feel like daylight compared to something else.
Yeah, because it was probably like 1% of the surface area of the sun was exposed.
Yeah, I would think something small like that.
And it felt like 4 p.m.
Exactly. Yeah, I mean, it felt like not even evening, because again, the light was very white. Like in the evening, you kind of get the evening color scheme where more blue is being absorbed.
Yes.
In this case, it wasn't that warm light. It was pretty cool, like full spectrum bright white light, but just less of it.
Wow. Now just so you know, you've now refilled me with regret for being in the wrong place.
Yeah. Well, there is one coming up next spring, so there's still opportunity to try to travel to that one. So with that set out, I guess let's talk about why and how these things happen. And for me, the first question was, why don't they happen either all the time, or at least what seems like, it would be all the time, versus it seems like they happen really irregularly. So what's going on there?
Yeah. I will summarize this, and then we got to dive into some details. But the reason this is so irregular is because the likelihood of an alignment of these planetary objects, of the moon and the sun,
and the Earth,
and the Earth, right? And specifically your position on the Earth,
yep,
is so small that not so A, it's infrequent, and B, it's very irregular because you have three different objects. You have the Earth rotating.
Yep.
You have the Earth orbiting the sun.
Yep.
And you have the moon orbiting the Earth, and you have tilt in the moon and the Earth.
Right.
In the moon's orbital plane and the Earth's own tilt. And all of these things combine to create honestly, to me, it feels like a dice roll. Like, it's predictable, but it's not regular and consistent.
Yeah, that makes sense.
Now, I imagine at like a multi-thousand-year scale or even like a million-year time frames, there probably is some rhythmic periodicity to this. Mm-hmm. But in a human lifespan or even in human history, I don't think the rhythmic periodicity is consistent.
It's not showing up. Yeah. And I think, there's some biases I had to this, and we were talking ahead of this. Like, I assumed they just don't happen very often. But Dave, you pointed out they actually happen. There is an eclipse somewhere on the Earth, visible on Earth, more often than I thought. And it's part of our bias is how much of the Earth's surface is not populated with people. Like, all the ocean and a lot of the landmass.
Yeah, in fact, it's I read that there's about, on average, a total solar eclipse happens somewhere on the Earth's surface about every 18 months.
Okay.
But given the fact that the vast majority, I mean, what, like 60+ % of the Earth's surface is water,
Yep.
and then of the remaining 35-40% of the Earth that's land, some vanishingly small percentage of that is actually populated by people.
Yep.
And then an even smaller percentage of that is close to big population centers where people would actually be interested to go and travel and see that.
Sure.
Nevertheless, I am aware of tour companies that will charter boats to take you out into the middle of the ocean so that you can experience a total solar eclipse when everyone else can't.
Very nice. And actually, that does remind me, there was one in China a few years ago, and I remember there was a company offering a flight package where they chartered a plane and they were going to fly a path that was meant to maximize their time in totality, because they could kind of travel along with it, and plus see it from 30,000 feet, whatever that would be like. So
That's interesting. And I think that just part of the mental model that helps to understand this is that I think as a kid, I thought about eclipses and I thought, oh, the entire Earth is cast into a shadow of the moon.
yeah.
But in reality, the moon is casting a relatively tiny shadow on the Earth's surface that's only about 170 miles in diameter. And that shadow moves across the Earth as the Earth rotates and the moon orbits and the Earth orbits the sun in a path that takes, I don't know how many hours it takes to cross, for example, the continental United States. But it's something like 6, 7, 8, 10 hours, something like that, to get all the way across.
Okay.
And so it's moving along, it's lumbering along the Earth, just tracing this shadow like a pen on the surface of the Earth. And so it's small. It's really little. And that, I think that probably plays a lot into why it's so infrequent. It's almost like shooting a laser pointer at the Earth and then hoping to trace the dot.
Yeah, exactly. And I think, I had that same conception that everybody saw the same thing. And it turns out it's, as you said, it's really not true. This is probably where we start to tiptoe into the details and talk about why this is such a delicate alignment. And this really comes down to, I think, the relative size in the sky of the moon and the sun.
Yes.
Yeah, do you have the numbers? I was wondering if you wanted to share the thought on how similar they are.
Yeah, this is probably one of the most interesting coincidences in our solar system, in my opinion. Now, it's the only coincidence I know of, so I'll just keep it there. But as a human being standing on the surface of the Earth, if you look up at the moon and you just kind of take a ruler and hold it up and measure the diameter
especially
of the
a full moon. Yeah, when you can see the whole thing.
Yeah, like a full moon, right? And we'll talk about this later, but there's some variability in the size. But when you measure the diameter holding a ruler at arm's length in front of your face, the size you will get is almost exactly the same size you will get when you hold up a ruler to the sun.
Okay.
Even though the sun is like 93 million miles away, and the moon is only 238,000 miles away.
So I'm doing some math. Just think about that in my head. So you said 93 million miles versus like a little less than 250,000 miles. Is that right?
Yeah, that's right. So the sun is 389 times farther away from us than the moon is on average. And those ratios of the distance between us and the moon and the sun are such that the relative sizes make them appear nearly the same size to us.
Yeah,
and that's why this works, because if the sun were any closer or any bigger, or if the moon was any farther or any smaller, we would never get a total solar eclipse.
Yeah, because it'd be too small. The moon's disk would be too small to fully obscure the sun.
Exactly.
And on the other hand, if the sun were smaller or farther, if the moon were closer or larger, then that shadow being cast on the Earth would be quite a bit larger, and these would become more common.
That's right. They'd be more common.
Yeah.
More common and more accessible. And frankly, I wish they were more accessible, because I think that's really cool. Imagine if the path were like hundreds and hundreds of miles wide. People would experience this a lot more conveniently.
Yeah. Though I wonder it's a really cool phenomenon. I also wonder if its rarity is part of that. Like, can you imagine if this happened every month?
Yeah, it'd be like, oh, it's eclipse time.
Yeah. Sorry, everybody. Football game has paused. We'll resume soon.
Yeah, every month there'd be like an increase in car accident statistics and...
Yeah. It is this coincidence. They're about the same size as viewed from the Earth. And in fact, coming up this month, we have an example showing just how fine that alignment is, and also representing some of the variability in the distances. So the Earth does move a little closer to the sun at a certain time of year in the North American winter, so in January. It's a little farther from the sun in July. I actually don't know the numbers, but I think it's a pretty small distinction. But the moon is also moving slightly in what we call an elliptical orbit, so an orbit that's not perfectly circular. Um,
Hmm.
and so it also gets closer to the Earth at times and farther at other times. So this must be one of those cases where the moon's a little farther away from us, and as a result, it's smaller in the sky, and as a result, it won't be able to fully obscure the sun. It's going to kind of pass through it and leave a ring around the outside of a visible solar disk. And that's called an annular eclipse because of that ring shape.
Yeah. And I've heard that's also really cool to see, but I haven't seen it.
Yeah, I don't think I've ever seen one either. So we'll have to decide if we travel, because that one actually slices not far from where we're at.
Nice.
I guess the next thing then is let's talk a little bit about the shadows that are cast and the geometry of this. So the way I think about this is the sun is much larger than the moon, but it's also very far away. And the entire solar disk is emitting light. And so in a partial eclipse all the way up to this annular eclipse coming up, the moon obscures some of that solar disk, but not all of it. At that time, one edge really all the way around in a ring, if you're in the center of that annular eclipse, there'll be a little sliver of sun, a visible sun kind of peeking around the moon. And if you think of the moon kind of moving towards the Earth and getting larger in the sky, as it appears to grow in our vision, it would then obscure more and more of the sun until the point comes where there's sort of no direct sunlight coming from the solar disk anymore. And so geometrically, we talk about these as tangent vectors, a straight line taken from, say, I guess, looking from the Earth's surface, looking up, the top part of the very top edge of the sun's solar disk, drawn across the top edge of the moon's disk, and that line will hit the Earth somewhere. And if you did this for every point around the perimeter of the sun, matching the equivalent point around the perimeter of the moon, you would be creating a cone shape. And
yes,
if the lines of that cone, they'll all converge to some point. That'll be the tip of the cone. And in the case of the annular eclipse, the tip of that cone actually converges before it reaches the Earth's surface. So everybody sees some little bit of sunlight peeking around at least one side of the moon. In the case of a solar eclipse, that cone has not yet converged to a single point when it reaches the surface of the Earth. And so essentially the intersection of that cone with the surface of the Earth defines the region of total eclipse at that point in time. And then, like you said, kind of like a laser pointer, that draws across the surface of the Earth over the course of that eclipse event.
And that drawing motion is due primarily to two things. One is the rotation. Well, I guess three things. One is the rotation of the Earth, because it's literally rotating out from under the shadow.
Yep.
But the other is that the moon itself is moving around the Earth, blocking the sun and then getting out of the way. And just like if you put your hand in front of a flashlight and you move your hand back and forth, but you keep the flashlight stationary, the shadow that your hand casts will move in proportion to how you're moving your hand. And then the third thing, which I think probably has the smallest effect, is the actual orbit of the Earth-Moon conglomerate around the sun.
Yeah,
because that's moving relatively the slowest, I think. I mean, not in like miles per hour terms,
right,
but in effect on the shadow terms.
Right. Yeah, because I think you can actually kind of derive it. We make a full solar orbit in 1 year, 365 days, and so we're doing 1/365th of that circle each day. So that's like 1 degree per day. It's pretty small.
Yeah, and that's not a coincidence that it's 1 degree, by the way.
Yeah. Exactly.
But that's a story for another time.
That's right.
But when you think about how long totality lasted for you in the total solar eclipse in 2017, was it a matter of minutes or seconds?
So we had moved close enough to the center that it was more than 1 minute, maybe as much as 2. But that was about it.
Yeah, so when you think about how far the Earth moves with respect to within its orbit of the sun within a 2-minute period, considering that it takes 365 days to make a full loop, It just has a very much smaller effect.
Yeah. Compared to the moon, which orbits the Earth in roughly 28 days, about a month. So.
And the Earth, which is doing a full rotation about its own axis every 24 hours.
Every day. Yep.
So it's like super fast. In fact, that's probably the biggest contributor to the motion of the shadow across the Earth.
Yeah, that actually makes total sense in orders of magnitude. It would be the rotation of the Earth first, the movement of the moon second, and then you have to be pretty precise to be able to account for the change in the sun's angle over that time.
Yeah.
So here's an interesting thought. What phase of the moon does an eclipse occur in? And in fact, what must it be?
So the second question you asked is actually the easier one to answer, I think. The other one, I guarantee you I'll get backwards.
Okay.
I don't know. Over the last few years, I look up in the sky every once in a while when I'm driving home or riding my bike, and I try to imagine myself and all the motions that are taking place to yield what we see in the sky.
Yep.
And it is very hard for me. And I don't know if it's just me or what, but I believe that the human brain did not evolve to track celestial motion. We're so bad at it. Like, I can walk forward, no problem. I can even walk backwards. I can throw a ball and predict where it's going to land. But when I look up at the night sky, I have basically no natural intuition about the way things are moving around.
I feel the same way.
With that, and I'll give just a little bit more preamble before I attempt an answer at your quiz question here, but I did a very long bike ride last month, and the bike ride took me all day.
Yep.
And so, when you're riding all day, you have a chance to observe things, especially the interesting phenomenon of the sun rising and then the sun setting, and you're still in the same kind of relative position on your bike, just pedaling along.
Yeah.
And so that was me, and I noticed in the morning the sun was coming up on my right, and I tried to imagine myself not watching the sun move over my head to the left, but rather imagining myself hurtling to the right.
Toward it.
To then meet the sun, toward the sun. Yes. And then in the evening, hurtling, continuing that same direction, but hurtling now away from the sun.
Yep.
And I just kind of imagined myself on the surface of a giant sphere, and the sphere was just rotating. It helps if I just imagine the sun stationary to do that. But that's more like, I think, what it takes to understand these motions is that things are not moving around the Earth. Well, the moon is, but rather you are yourself on a rotating sphere that causes most of the motion that you observe in the sky, including sunset and these moon phases. So let's go back to that. So for a solar eclipse where the moon completely blocks the sun, what must be the case? Well, it must be the case that the moon itself, and I'm actually going to hazard a guess here, and I'm expecting you to correct me, but the moon itself is not at that point illuminated by the sun directly.
Right.
In fact, you are viewing from the Earth's perspective the dark side of the moon.
That's right.
Because it's about to go between you. The moon's about to be oh man, see what I mean? Even our language, I was about to say the moon is going to go there, but the moon's not going there. You're just rotating into position, right? Well, it was already pretty close to there.
Yeah, but it's going there slowly. Like
it's going there slowly, but we're going there 10 times faster.
Sure. Right? Yep.
So we're moving there at 10 times the speed that it's moving just by rotating into position to see it. And it is darkened by the sun, meaning that the opposite side of the moon from you is the side that's lit up by the sun.
That's right.
And so what's that called? That's called a see, this is where I can't answer whether it's waning or waxing.
Yeah. So it's neither. That is a new moon.
Okay, right. Got it. At that instant where you perceive the solar eclipse, that is the moment where a new moon just took place.
That's right. Yeah, right? If you were going to very precisely measure when you finished being a waning crescent, meaning the moon's illuminated surface visible to the Earth got very small, and you're going to then really the next day begin your waxing crescent when it begins to become illuminated again. The in-between, lasts about a day, is the new moon. Mm-hmm. And so it's during a new moon that the moon, Earth, sun are in the right relative positions for this type of eclipse to even occur. And then, as you said, it's up to the Earth's rotation to pull you into the position to view it.
Got it.
So then what about a lunar eclipse?
Yeah, so this is the exact opposite, because when the moon is on the other side of the Earth from the sun, meaning that the Earth is between the moon and the sun, that means that when you view the moon, like imagine the moon is just slightly off center from that line between you and the sun. Mm-hmm. The moon is not collinear with those two. It's actually off just by a few degrees.
Yep.
What that means is that the face of the moon that you're viewing from, and again, now at this point, you're on the opposite side of the Earth from the sun.
Yep.
And you're looking up at the moon, but it's all lit up.
Yep.
And the reason it's lit up is because those rays from the sun are flying past the Earth and then hitting the moon, and then you can see them because they're reflecting back toward you down on the surface of the Earth.
Exactly.
And so that is a full moon.
Yep. Exactly. And so these two events can only occur in those respective phases. And kind of like you talked about when you were on that bike ride, and based on your description of the sun rising over your right shoulder, setting over your left shoulder, I think you must have been biking north in the northern hemisphere.
Good intuition.
And actually, the hemisphere wouldn't matter for that. And I think you hit on the head when you say human beings aren't maybe innately equipped to understand these orbital mechanics. And in fact, I think there's good evidence for that. I'll say it colloquially first, and that is, we're so used to ourselves kind of being the center of things and seeing relative motion around us. We assume everything that's moving in our field of view is because that thing is moving. And so in that case, where am I going? For a lot of human history, people assumed the sun was rotating around, or was revolving around the Earth. And in fact,
it sure looks like it, doesn't it?
It does. And you see that. And so intuitively, it seems like the right thing. And of course, this became, a point of serious contention, and people lost their lives over pointing out that there was actually a more consistent answer, which is that the Earth was revolving around the sun. And so we kind of take that as granted now. But I mean, what was it? Less than 500 years ago or so that this was really being sorted out? Maybe 1,000 years ago.
Just a blip in the historical record.
Yeah, exactly. And so same thing. I look at the sky and it just is what it is. And again, if I were more curious about it sooner, maybe I would have developed an intuition faster. But one thing that started to make sense to me was when I started to notice the correlation between the time of day that the moon rises and sets and the phase. And for me, that was what made it click and made me realize, oh yeah, and it makes total sense. The moon's orientation relative to the sun is what defines the phase. When the moon is in the same direction as the sun, it's a new moon, and a new moon's going to rise in the morning and set at night. So it's in the sky during the daytime. On the opposite side, a full moon is when the moon is on the Earth is between the moon and the sun for the most part. And in that case, the full moon is going to rise around the time the sun is setting, give or take, and it's going to set around the time that the sun is rising, give or take. And then the intermediate phases, essentially are offset accordingly. And so over the course of a month, when the moon is going through these phases, an interesting thing, think about the word month and the word moon.
And the word moon.
Yeah. And the fact that the moon's, cycles roughly 28 days, maybe 29, and months are roughly 30 days long. Over the course of the month, the moon makes one full orbit around the Earth. And so the way it does this is every day the moon rises like 40 something minutes later. So that's another thing you'll kind of notice is you see the moon rise one day, and then especially as it's getting close to a full moon, so it's rising in the evening. The next day it's going to rise not quite an hour later, but maybe 45 minutes later. And
that makes sense because it takes 28 days to complete its cycle, but there's only 24 hours in one of our days.
Exactly.
So just a little bit less than an hour to change each day. Okay.
Yeah, so now it starts to make sense, right? In fact, now I'm wondering where the hour came from and why there aren't 28 hours in a day. Because
I know. It would have been so much better.
Yeah.
And it could just be an error in a lot of these measurements. I mean, the fact that we have 30 days in a month instead of 28 days could be error. The fact that we have, almost 12 or a little more than 12 lunar cycles in a solar year could also just be measurement error. But we just stuck with it.
Yeah. Actually, I was thinking about this the other day. I didn't do the math, but I've wondered if there actually would fit 13 lunar months in the year.
There do. In fact, it's so close. It's 364. So if you take 28 days times 13, you get 364. Oh. And just a little tangent, no pun intended on the tangents. Nice. But my favorite calendar is this idea that we can have 13 months, 28 days long each, and then we'll have one holiday that's not part of a month. That's New Year's Day every year.
Oh, that's awesome.
We do need leap years, and so some years you get 2 holidays.
Oh, all the better.
And every day of the week is on the same days of the month.
Oh, yeah, because they're 28-day months then, which is
and 4 7-day weeks.
Oh, my goodness.
It is the most beautiful calendar on Earth, and if I were a dictator of the world for just a day, I would wave my wand and do that.
That is awesome. Yeah. Okay. So What else should we talk about here? I think
Well,
that's
there's something we left out that I think is going to make the mental model hard to form for everybody here.
Okay.
There is an important relationship between all of these orbits. So we have the two orbits that matter in this case
Yep.
are the Earth going around the sun and the moon going around the Earth. And I was embarrassingly old before I knew that the orbital plane of the moon around the Earth, in other words, the imaginary flat plane that this thing traces out as it
Yep.
goes around the Earth, is very closely aligned to the orbital plane that the Earth traces out as it goes around the sun. They're like two planes that are super close. Imagine, if you will, if the moon went around the Earth and formed a plane that was like perpendicular to the sun.
Yep.
That would get all kinds of jacked up. But I mean, and now that I'm an adult with a thinking brain, I realize this makes no sense at all. The moon would start getting pulled into the sun.
Well, but hold on to that, because I'm wondering, there are planets whose rotational axis is way offset. Like
yes, now that is okay, right? Like that doesn't
Yeah.
mess up the galactic order of things.
But do they have moons? And what do the moons do? I'm thinking like Uranus. Is that one of the planets that does that?
That's a great question. And as we get into those, I think we do need to acknowledge that the two orbital planes we're talking about, of the moon and the moon around the Earth and the Earth around the sun, they are not exactly aligned.
Yeah.
They're not perfectly coplanar. And so that leads to all kinds of interesting variation. And then there's a third plane that is interesting for people who want to figure out where to go to see these eclipses.
Mhm.
And that is the Earth's equatorial plane, which itself is offset from, it's not coplanar with these two planes either.
Yeah.
Or I should say it's not parallel with those
Yeah.
planes either. And so first, and we'll get, well, I think we're going to talk more about that in a minute. But before we get to that, just wanted to point out, this is why on the Earth, as it revolves around its own axis, or rotates around its own axis,
Yep.
and it orbits around the sun, and the moon orbits around the Earth, we can see this phenomenon where the moon is usually in very consistent positions in the sky. And it kind of wobbles up and down throughout the year, but it generally comes up in the same place and sets in the same place. But it has nothing to do with the time of day. Whereas the sun always sets in the evening and rises in the morning, but the moon does not rise in the morning and set in the evening.
Yeah, it's based on the phase as it makes that monthly revolution. So yeah, that's a good point, because let's make a fake Earth, Moon, Sun system in our heads for a second and think about the consequence, and then we can go into what all these other effects actually are. So imagine if all of this was in total alignment. So imagine if you had the sun at the center, the Earth is revolving around the sun on an orbital plane. And then imagine if the Earth, so as you talked about the Earth's axis of rotation, like our polar axis, or another way to put it, the equator, which is the ring that's perpendicular to the polar axis that circumscribes the center of the northern and southern hemispheres of the Earth, if that were parallel to the orbital plane, so imagine the Earth is like, call it perfectly spinning upright like a top.
Exactly.
Then, first of all, we wouldn't have our conventional summer, winter, long day, short day cycle. Every day would be the same. Right. And then if you were to put the moon on that same orbital plane, orbiting around the Earth, we would actually get an eclipse every month. We'd get a solar eclipse on every new moon, and we'd get a lunar eclipse on every full moon. And that path of totality would always trace along the equator, because it would all be perfectly aligned.
We would all have to travel to the equator to see it, but you could do it every month.
You'd know
every 28 days.
That's right.
Yeah.
That's right.
I'm sure it would be a really awesome tourist destination, and it would be like this crazy seasonality where at the end of every 28-day cycle, you have all these tourists come in and then they're gone for 27 days.
Exactly. Talk about boom and bust.
Yeah.
And so if we start to introduce the variables back in, the realities, then this starts to explain why these are less frequent.
Let's introduce each variable. So one at a time and talk about the effect. And then I think we're going to see the multiplicative effect that creates why these are such a scarce event for us to perceive.
Yeah. So probably the first one that I guess we could choose either order, but I'm thinking if we first talk about the moon's orbit and how it's not exactly coplanar with the Earth's orbit around the sun.
Okay.
Because that's what results in the moon's shadow not hitting the Earth on every cycle. You talk about a total eclipse happening every year and a half or so. And so the moon, I think, has like a 5 or so degree offset relative
Yes.
to that solar orbit or the Earth's orbit around the sun. That orbital plane is called the ecliptic, which makes sense because that's where you have to be to get an eclipse, is on that plane. And the moon, I guess, is tilted about 5 degrees off of that, which means that some of the time the moon is as many as 5 degrees kind of above that in some frame of reference, and as many as 5 degrees below that at other times. And it's only when the moon is crossing from one side of that plane to the other, crossing through the ecliptic, that the shadow that it's always casting will actually have the opportunity to hit the Earth. And so
Yeah.
that has to come into alignment.
This one kind of surprises me. So you're saying that the moon, as I look up in the sky, at a maximum offset, is only 5 degrees off from its average path around the Earth.
Be careful. So we haven't.
saying?
No, it's 5 degrees off from where we perceive the sun to be.
Yes. Not from the equator.
That's right.
But rather from the sun's orbital plane.
Yeah, from the Earth's orbital plane relative to the sun, which defines
Yes, of course,
how we
sorry.
see the sun. It's this whole frame of reference thing that's really hard to wrap our head around.
Okay, so that 5 degree, call it a wobble,
Yep.
causes the moon's shadow to literally miss the Earth.
Yep.
On most of its orbits around the Earth.
Exactly. Because it's either above or below the line between the Earth and the sun.
That's incredible. I mean, only a 5 degree mark. Because, like we said before, if everything was perfectly in alignment, it would be happening every 28 days. The shadow would be tracing across the entire half of the Earth's surface along the equator.
Yep.
Take
exactly.
a 5 degree wobble away from the Earth's orbital plane, and now it only happens every 18 months.
Yeah, and the reason is I think it's still crossing, regularly, like probably every orbit, but it has to cross at the same time that it's in one of the two critical phases, either
new moon or
full moon. Yep.
Yes.
Exactly. And so it's the combination of those two events having to occur at the same time that makes it so infrequent. And then the third factor being wherever that shadow is being cast, if it's in a place where there really aren't any people and it's hard to get to, then it becomes less of an event in our minds.
Yes.
And so we're aware of the ones that hit populated areas, easily traveled to destinations. And so that's what makes them feel like they only happen every few years, at least in my popular consciousness.
Now, there are other factors here that cause the eclipse events to be even more scarce.
Okay.
But as I say that out loud, I'm now questioning it. So the other factor I immediately think of is the Earth's tilt.
Okay.
So this is what you were talking about earlier, the poles of the Earth. If you draw a line from North Pole to South Pole, that line is not 90 degrees offset from the Earth's orbital plane.
Right.
It's 23 degrees?
23.4. Like I think of it as 23 and a half. I think it's 23.4 something.
Does that contribute to the scarcity of the eclipses, of the eclipse striking a shadow on the Earth?
I don't think so. I think what it affects is just where it's going to hit and making it even harder to predict where it's going to hit unless you model all of these factors together.
Got it. Yes, I was just thinking that myself. So that contributes probably more to the frequency for any given position on the Earth of experiencing an eclipse.
Yep.
But it doesn't change the fact that, that shadow's still going to hit the Earth somewhere every 18 months.
Right. Exactly. Yeah.
Okay.
And so I think it just, it expands the diversity of where that shadow will land.
And frankly, makes it seem more random.
Yeah.
In my opinion.
I think so.
Even though it's totally not. These things are 100% predictable for probably centuries, if not millennia.
Yeah, I would expect so. And so then, and I guess one other thing that makes it a little less common to have a total eclipse is, next week's or the week after's being the example where the moon has to be close enough to the Earth to cast a large enough shadow to fully obscure the sun. And so in near term here, we're also at the wrong point in the Earth's elliptical the moon's elliptical orbit, where it's a little further away. And as a result, it won't be total. If this was the part of the ellipse where it's closer to the Earth, we'd be talking about a total eclipse here in the next couple of weeks. So it's the convergence has to be in the right part of of the elliptical orbit, has to be crossing through the orbital plane of the Earth around the sun, the ecliptic, and has to be at the right phase, meaning it's at that full moon phase for a solar eclipse. Yes. And so now when you take all those factors together, you're starting to talk about something that's much less frequent.
Exactly. And I think the statistic I found was that for any given point on the Earth's surface, these shadows from a total solar eclipse only come around about every 400 years.
Wow. Yeah, so you think about up until the last little while, when humans haven't had the ability to travel in the way that we do, and certainly didn't have the way to predict that this was going to happen at all. This would have been an extremely rare event. Most human beings would never experience it, and the ones that did, would have been pretty concerned about what was going on that day.
Yeah, but knowing humans like I do, because I am one, I promise. They only last about a minute, and then they're like, "Oh well, that was weird. Let's get back to work."
Yeah, remember that time that weird thing happened? Well,
no, I can't remember. What are you talking about?
Yeah, exactly.
I mean, we build these things up in our own minds because we know they're coming years in advance, and we prepare and we buy flights and we make them more meaningful. I just have to imagine that people who they happen to, who didn't know they were coming and didn't ascribe any pre-meaning to them, like pre-planned meaning, probably thought, "Holy crap, that was weird. Was that like a big flock of birds or something?" Like,
right,
what was
right.
that?
Did
a really dark cloud?
Yeah. Did I eat something weird today? Like, did this actually happen?
Yeah.
Cool. Well, I think we actually hit the key points here, Dave. Anything else you want to talk about with respect to eclipses?
No, I think we got it. So to just sum up, all these factors make eclipses not happen every month. They are or not happen every month in the same place for sure, and not even happen every month anywhere on Earth. As well. And they are the misalignment of these orbital planes between Earth, Moon, and Sun. They are the elliptical nature of the Moon's orbit. I suspect that the Earth's ellipse doesn't really have much to do with it because it's so tiny in comparison to the distance the Sun is away from both the other bodies, right?
Yeah, that's a good one. Yeah, maybe it'd be a little more difficult in January when we're a little closer to the sun. Sun going to look a little bigger, but I actually don't know how much bigger it appears in the sky compared to summer. But yeah, that would be a factor as well. And
then the Earth's tilt makes it seem more random, but doesn't actually change the frequency of eclipses hitting the Earth.
Right.
At some point. And then just an interesting fact that actually plays into this not at all is the fact that the moon itself also has a tilt in its own rotation around its axis. And its own rotation around its axis is totally locked with the Earth's rotation. So we always are facing each other. The moon is always facing us.
Yes.
Even though we are not always facing the moon. So the moon actually gets a better view of Earth than Earth gets of the moon.
If you're on the right side.
We've never seen the backside. Yeah. That's true.
The other half of the moon. The other half don't even know there's an Earth. The people that live on the dark side.
They know there's a sun.
Yeah.
Wouldn't that be amazing if the Earth had a locked orbit like that with the moon and only half the population knew there was a moon on the other side? And then they show up and they say, "You'll never guess what we see in the sky every night."
That's right. Like no one would believe them.
So there's all kinds of interesting motions and tilts and wobbles and stuff, and only some of them affect this.
Yeah.
But the ones that do affect it, man, they really create an awesome experience.
Absolutely. So since you went there, I can't help it but just chew on this title thing a bit. So
I knew it. I've been thinking about tides the whole time.
Okay. We've got the moon, we got the sun. We actually laid out all the orbital dynamics. We really owe the tides a discussion. This could be like bonus afterward.
You can stop listening now, but if you don't, enjoy. And I gotta say, Shane, I have studied tides several years ago when I lived on the East Coast in New England, and I was trying to understand the tidal forces. I watched all kinds of videos and read all kinds of material. I just have to be honest, I don't get them.
Okay.
The way they behave and the way they're described to behave does not match my mental model at all.
Well, let's see how far we get, because I claim I don't fully understand them either, but at least some aspects of their schedule make sense to me.
Yes, well that I get too. But
so anyway, I think we can talk about the schedule. And actually, I sort of only half meant to introduce the word tide, but when you talk about how we see one side of the moon, and that's because as the moon is orbiting the Earth, it's rotating at exactly the same angular velocity, and so it's always kind of facing inward, if you will, toward the
meaning it takes 28 days to complete its own rotation.
Yep.
And it also takes 28 days to go all the way around the Earth. And thankfully, it's rotating the right direction. I don't know if you would call it clockwise or counterclockwise, but if it was going the opposite direction, we would actually see both.
Yeah. So
the fact that, by the way, from what I've heard, the fact that it faces us all the time is not a coincidence.
Correct.
Because it's doing exactly what would happen if a chunk of the Earth had broken off, and they were both spinning when they started.
Yeah, that's one way that it can happen. So few things here. That's when this happens. I think it's called tidal lock. Like it's locked in, And I think of it like swinging like a tether ball, holding the string, like the
Yeah.
the string to the ball is always facing inward. And so if you were just
Yep.
looking from above, you would see the ball rotate, revolving around the center. But you also would see that if you think about it, the ball is in fact making one rotation as it makes each revolution, because that string points inward the whole time. And that's what's happening with the moon.
Except in the case of this analogy, the tetherball pole is itself rotating as well on a different
Yeah.
schedule.
Yeah. So like more like if I'm holding the ball with the string with my hand, I guess, and like swinging around kind of with it. But yeah,
Yeah, exactly.
these orbiting bodies, the moon and the Earth in particular in this case, they have they're of course bound by gravity. That's why the moon is orbiting the Earth in the first place. And that gravity doesn't just affect the object as a whole, even though when we first learn physics, like we simplify things like that. The gravity is actually affecting every particle of each of those bodies, and the result is it's pulling all of those particles kind of toward each other. So the Earth is pulling the moon toward it kind of piece by piece, and in net effect, it's causing the entire object of the moon to rotate around the Earth. And similarly, the moon is pulling all the squishy soft parts of the Earth toward it. And in particular, we see this in the form of our oceans being sort of dragged by the moon toward it, which means that we get tides where the ocean rises at some part of the day and it goes down at a different part of the day in harmony with really the relative position of the moon as the Earth is rotating around its axis. So this isn't due to the moon. The fact that the tides go up and down is not due to the moon orbiting around the Earth. The moon is almost stationary in that context of the daily tide cycle, but there are 2 high tides per day and 2 low tides per day. So you can think of like the water, again, I think the squishy part of the Earth, which the water is very much so, it's being pulled toward the moon, and there's kind of this counterweight on the backside of the Earth away from the moon. And as the Earth is spinning, it's causing that bulge of water to kind of keep being pulled by the moon. And then there's going to be a phase offset due to, this is where I'm outside of my realm, due to the particular dynamics of the particular system. But a common property with systems is if you sort of wiggle them, they have what's called a resonant frequency, and you kind of wiggle them at that frequency and they'll vibrate a lot. And they might not vibrate in the same phase as your input, but they'll vibrate at the same frequency. And so the tides are oscillating at the same frequency as the Earth's rotation relative to the moon, even if they're not perfectly in phase with the moon. And so if you look at a tide table, what you'll see that there are 2 high tides per day, 2 low tides per day, and day over day, those shift.
I want to interject here.
Go.
I want to guess.
Go.
I want to guess.
Yep.
Because I think earlier we had said that the moon rise is about 40 minutes each day different than the previous day.
That's right. Yeah,
and I'm going to guess that the tidal change, like if the high tide came in at 8 a.m. today, tomorrow it's going to come in 40 minutes off from 8 a.m.
That's right. Yep. It's going to come in about 40 minutes later. Again, it's not always perfect, but approximately the tides happen a little bit later every day because the moon rises about 1/28th of a day later every day as it's making its orbit. So that's one effect you'll see is you can kind of guess, okay, today if there was a high tide at noon, tomorrow that high tide is going to be closer to 1 p.m. And so if you're trying to figure out the sequence with the ocean, that's one kind of mental model you can have. Another thing that'll happen is that you'll go through a series of different types of tides. There are what are called spring tides, which are where it's a higher high tide, a lower low tide, so it's a bigger oscillation, and then neap tides, which are smaller oscillations. And this, do you have a guess what phenomenon define spring tides versus neap tides? And what?
Yeah, probably the same thing that defines what we haven't said yet, which is the supermoon, which is the elliptical shape of the moon's orbit around the Earth, where it's actually a little bit closer or a little bit farther away at different phases.
That has an impact, but the bigger impact is actually the phase of the moon itself. So when you have a new moon, and you have the moon and the sun. So it turns out the sun also impacts tides on Earth.
Oh, yes.
Quite a bit of gravity there too. And so
yes,
it's when the sun and the moon are pulling together. And
oh my goodness.
So you get 2 spring tide cycles per lunar cycle when you have a new moon where the moon and the sun are pulling in the same direction. So the moon is between the Earth and the sun, between the sun and the Earth. That pulls harder. They're pulling together. And then as the moon over the next week passes through the waxing crescent and it gets to be, and this is something
halfway to the full moon.
Halfway to the full moon, which to me geometrically looks like a half moon, but it's called first quarter. And this makes me crazy because half of the moon phases are described by what the moon looks like, and the other half are described by how far around the period of the moon you are.
Oh.
So you go from a new moon, which is zero moon, to a half-filled moon, which is called first quarter, because you're a quarter of the way through the cycle.
Right.
And that's neap tides, because now you have the sun and the moon working against each other. They're perpendicular to each other.
Right. They're orthogonal. In other words, they're pulling.
Yeah.
This is the part that I don't understand, actually.
They're pulling out of phase. And you have to remember again
Yes.
that there's this kind of double bulge where part of the ocean is pulled towards the moon, and then there's like this counterweight on the far side of the Earth that's away from it. And so then you have
And this is the part I've never been able to understand.
Okay, I'm trying to think if I have a good way to explain this or not. I probably don't. But it's, yeah, so essentially I think of it as almost like if you think of a sphere of water and you kind of squeeze and stretch it so it becomes elongated. You don't just pull a bubble to one side. You actually like make it wider on one axis and narrower on the other, and it kind of oscillates between the two. That's kind of what the tides do.
Mm-hmm.
And anyway, the moon's doing that on one axis. The sun is 90 degrees offset, doing it on a different axis. So they kind of work against each other, and they make for a smaller total oscillation. And then over the next week, you've gone from that first quarter, the half-filled moon. It's now a gibbous moon because it's more than half full, and it's waxing, it's growing. And so it waxes to a full moon. And when you hit full moon, now the sun and the moon are on opposite sides of the Earth, but they're sort of like pulling back and forth at least in phase. They're time aligned. And so that bulge stretches out again, and you get another set of spring tides. So higher tides, higher highs, lower lows. And then from full moon, it begins waning. It's a waning gibbous until it gets to third quarter phase. The moon's half full again. And then from there, you get the waning, and so now you have neap tides, and then you have the waning crescent back down around to a new moon, over time the tides are growing in that week again until they hit spring tides at the time of the new moon. So if you know the time of day that the moon rises or sets, or you just see it in the sky and you look at its phase, you can actually predict if you're going to have big tides or small tides. And then if you know when that, say, biggest high tide of the day is, you can kind of predict roughly when the subsequent high tides over the next few days are going to be, based on that knowledge that it's going to be delayed by, not quite a full hour, a good chunk of an hour, 40, 45 minutes or so per day. And so that actually gives you quite a bit of predictive power at that point.
Amazing.
Okay, so last thing, the tidal locking. Sorry. Where's this all going? That moon pulling and stretching on the squishy parts of the Earth actually creates friction, and it creates a torque. And what it essentially does is it encourages the rotating body, in this case the Earth, to either speed up or slow down so that its rotation aligns to the orbit of the moon itself. And in the other direction, the Earth is exerting very strong tidal forces on the moon, because the Earth's a lot bigger than the moon. So you think about how much the moon pulls on our tides. Imagine if the moon had water on it. The Earth would exert a tremendous tidal force on that. Well, the Earth even exerts a tidal force on the Earth, or it's not the Earth, the rock, the solid material of the moon. And apparently it can cause enough like internal friction and whatnot to provide enough torque to, at least once you're in this tidal lock state like we're in, to keep it there. Like if you tried to start spinning the moon a little faster, it'll actually slow back down.
Amazing.
So that it stays in alignment. And I think there are...
I knew the term tidal lock, but I did not realize that it was actual tidal forces that are keeping the moon in its rotational speed.
Yes. Exactly.
Incredible.
That's what keeps it stable. And I think...
do the other moons in our solar system have the same effect? Are they also tidally locked to their planets?
I don't think all of them are. I think some of them aren't even... I don't know, actually. I'm going to stop.
I wonder if they're in progress, like on their way to becoming tidally locked.
Right.
Over time.
Yeah, I think some, maybe Venus in our solar system is, if not tidally locked, is near tidally locked. Like there's its atmosphere is kind of stretched and spinning at a certain speed, and I think that affects it as well, but it happens at a planetary scale as well as at like lunar scale.
So according to NASA's website, all the big moons in the solar system are tidally locked. Amazing.
Yeah. Because I had always assumed it was because it was a chunk of the Earth, and it makes sense they would start with the similar
I
angular
did too.
momentum. But
But I thought about that, and I realized like it doesn't actually make sense that they would stay locked facing each other because the Earth doesn't face the moon.
Right.
And I don't know what the current theory is on the moon breaking away from the Earth or not.
I don't either.
But if they broke off from each other, it would make sense that they both faced each other permanently.
Yeah, possibly.
Or would it? No, I guess because you break something out, its orbital speed
but
goes
actually,
slower
Dave,
because it's further away.
but actually, and you know what? Thinking this through, like the moon is not rotating at the speed that the Earth is not orbiting at the speed of the Earth's rotation, which would be what would happen when if it call it first broke off.
Exactly.
Like it orbits on a monthly cadence, and it has settled into that monthly rotation. Which again, if you're sort of you can imagine maybe there was a cloud of dust that I don't know that there's enough gravity to have that like consolidate into an object. So total speculation. I'm sure other people have studied this and have better thoughts. But the stability of that situation and the ubiquity of it, like you said, all the big moons, I would guess that notion is significant. Like they have to be big enough for this tidal force to actually be meaningful, which means you probably have to like a small thing is going to be acted on like almost a single object, from a gravitational perspective. But a big thing actually has, a more broad integrated pull being applied to it by gravity. And I would guess that plays a role in this tidal lock stability that occurs. Well, cool. So
okay, well,
we started with eclipses.
Plenty of bonus material.
We started with eclipses. We ended up with why does the moon have, if not a dark side, at least an obscure side from Earth's perspective. So that was a good journey, Dave.
Okay, thank you, Shane. I absolutely loved it as usual. Thank you so much.
Same here. Talk to you later.